In this presentation, I'll talk first about parametric and non-parametric statistics, how to increase the robustness of your results and your presentation, bootstrap and the permutation method, correction for multiple comparisons, and statistical analysis using GLM, everything in under 1 hour. And first, take-home message. If you remember anything from that presentation, look at your data, show your data around. There's no perfect and universal statistical recipe. It depends on your data, the length of your epoch, if you're looking at continuous data, and keep exploring for new methods. So we're going to talk mostly about inferential statistics, but also confidence interval. So a typical null hypothesis, if you have two conditions, for example, is that there is no difference between the two sets of values. And you have a null distribution, so H0 is a null hypothesis. And then we look at the tail. Is our actual measure in the tail of that distribution? And if it's the case, yeah, we have a p-value below 0.05. We're done. Well, not so fast. So if we make that inference, we have type 1 error, so that's usually our statistical threshold. But if we accept the null hypothesis, if we say there's no statistical difference, we can't really deduct that there is no effect. And that's the type 2 error right here. So that's important distinction to do. Absence of evidence is not evidence of absence. You have to look at the type 2 error. Also, a very important concept that's often overlooked in statistics. We focus on the p-value. What's my p-value? It's the effect size. So effect size here on top is effect size of 0.2, and that's a small effect. Here, effect size 0.5, called medium effect. Effect size 0.8, large effect. And you see there's still large overlaps between the two distributions. This is assuming the distributions are Gaussian. And it's very important because if you have enough data, let's say you have million trials, billions of trials, everything becomes statistically significant. Every small factor you might look in the data, temperature of the room or anything, everything is going to become significant. It's going to have extremely low effect size. So it's not really worth reporting. So that's why when you report your p-value, it's also very important to report the effect size. Also, if you submit a grant proposal, you'll be asked to do a power calculation. And the way you do a power calculation is that you look at the literature and you try to infer, okay, on my oddball p3, what's my expected effect size based on the literature, or whatever you might be studying. You enter that. There's websites and packages, and you can enter your effect size, your desired significance level, and it's going to give you your sample size. Usually, a range between 16 to 32 for neuroimaging analysis. And that tells you that if you acquire that much data and you assume an effect size of 0.2, say, you need that many subjects. So we're going to move to parametric statistics. We all know and love pair t-test and pair t-test. These assume Gaussian distribution. And there's actually many more of these formula. So in the center here, we have all the most of the parametric measures, repeated measure ANOVA, and we have also the equivalent when we look at the rank of the data. So these are called non-parametric statistics. So Madden-Whitney, so they're basically equivalent to parametric statistics, except they look at the rank. And then we also have a bunch of statistics, chi-square, etc., when we have binomial data, so discrete data. This is the difference between parametric and non-parametric statistics. On parametric, you have the pair t-test rank, you have Wilcoxon, and pair t-test, Mann-Whitney, one-way ANOVA, Kruskal-Wallis. You're usually advised to, these are more robust to outliers, But what's important here is that they still both assume a normal distribution. In both cases, the normal distribution of the rank. So how can we improve the robustness of our data, of our results? Well, the first thing we can do is try not to cheat in the official way. So when you pre-register a study, let's say for 40 subjects, you might be tempted, I'm going to compute my p-value along the way. Here, I have like 16 subjects. Let's just stop here. It just passed the threshold. But if you do that and you don't correct for multiple comparison, you're actually doing multiple comparison here. Every time you have a new subject, you might be calculating a p-value. That's a form of what's called p-hacking. You're hacking your data, basically, if you don't go with the number you plan with. So this is called optional stopping. And there's also ways to report your data. So for example, here we have 2 conditions, 1 and 2, and this is like a standard way people might be reporting their data. This is the significance between these 2 conditions. Here in this region, they're significantly different, and here they're not, except for here, these small points. The issue with this is how many subjects are here. We don't see it in the figure. What's the effect size? We don't see it either. What's the statistical power? And also, this is easy to overinterpret. So how can you make it better? Well, first we can add confidence interval. So we can add the 95% confidence interval. That gives us an idea of how different the conditions are. Then we can also subtract the 2 conditions and plot the 95% confidence interval of the difference. And here we have the region for which it is significant. Other things you can do is to plot every single subject trace, because then here you have an idea of how many subjects are present, and then also the proportion of subjects which shows an effect in the right direction. So it starts 0.5, and then it increases to 1 in these regions. And all of this reporting just makes it easier for people to interpret your data. Also, most people use the mean to compute central tendency. The issue with the mean is that it's not a robust estimate of central tendency. And for this, it's better to use the median or the trim mean. The trim means is you remove outliers and then you compute the mean. For example, 20 trim means provide high statistical power. In a lot of our analysis, we use the trim mean, for example. So still there are problems to just using parametric statistics. You're often not resistant to outlier. For ANOVA and t-test, non-normality is an issue, especially when you have distribution with heavy tails, and slight departure from normality can have serious consequence. So now we're going to move into the bootstrap approach, and most of the bootstrap approach comes from this book, Introduction to Robust Estimation and Hypothesis Testing, from Rand Wilcox. So the bootstrap approach, what's the bootstrap approach if we don't use parametric statistics? So the bootstrap, it's a computer-based method. And also, the central idea is that the best estimation of your distribution is your data. So that's what this second quote says, basically. So if we have here, this is our sample, and this is the distribution of values in our sample, we can make here the assumption that this comes from a Gaussian. So this would be parametric statistics. This is the probability sensitivity distribution of the population. And in Bootstrap, what we do is that we assume that the probability density distribution of the population maps the one in our sample. So that's the basic assumption, the best estimate we have for the probability density distribution of our data is our sample. So it can take any shape. Now let's look at some example how to compute Bootstrap. So this is from Rand Wilcox's book. Here's this percentage of self-awareness data, and we're going to compute the confidence interval for these measures. And these were just questionnaires, and they entered a number from 0 to 19. And you can see here's the number of answers. And so what we do is we sample with replacement, and we compute an estimate. So we sample with replacements, meaning we're going to take 1,000 value here, and every time we take a value, we put it back. And these are our bootstrap measures. So every single dot here is a bootstrap estimate. We draw randomly from the data, compute the value, draw again from the data, compute another value. And you see they're all over the place. So what we do is that we're sorting these values. So these are the same values, but here they're sorted from lowest to highest. And we can also compute here the histogram of the values. And then we set some threshold, upper threshold and lower threshold. And that gives us the 95% confidence interval of our data. Now, the good thing with this is that we can also do inferential statistics with this, because we can say, okay, these values are significantly higher than, let's say, this lower value here, 3. So this is significantly higher than 3. So not only we get the confidence interval, but we can also do inferential statistics. And the distribution can take any shape. We're just looking at the tails. So now let's try to compare two conditions. And so we have a set of value for condition A, a set of value for condition B. We analyze, which can be taking the mean, for example, compute the difference, and we have our value of interest. So this could be the ERP amplitude for 6 subjects, ERP amplitude for 6 subjects in another condition, computing the average ERP and taking the difference between the ERPs, for example. And we want to know if there is a significant difference between the ERP of subject in group A and group B. So what we do is that we put all these values in a bucket right here, and we're going to draw from this bucket and reconstruct our original samples. So we're constructing the first sample. Here we take A2, B1, B7. So we just draw randomly. But what you can see is that we can take twice the same value. No problem, because this is sampling with replacement. And so now we reconstruct our group A, not real group A, fake group B. We redo the analysis, and we get our first bootstrap value. And we're going to do that many times. So we do that a second time. We do that 1,000 times. So as before, we have all of our bootstrap values, about 1,000 of them. We sort the value from lowest to highest. We compute the histogram here, and we set some thresholds, and then we assess if 0 is in the tail or not. If 0 is in the tail, then you can say there's a statistically significant. We can even compute the p-value based on the position of 0 in the tail. Also, what's important to note here is that if the data is truly drawn from a Gaussian distribution, this will be equivalent to using parametric statistics, except here we don't make any assumption about the distribution. So even if it's non-Gaussian, it will work. What about paired value? So instead of having 2 groups of subjects, we might have ERP for condition 1 and ERP for condition 2 in each of the subjects. So this is, for example, ERP for condition 1, subject 1, ERP for condition 2 in subject 2, etc. Well, in that case, what we do is that we subtract these values, and we're going to bootstrap this distribution. And again, as before, so this is bootstrap iteration number 1. Again, we can take twice the same value. Here is the A3 minus B3 is there twice. We take the mean in that case of the difference. We get our distribution, and we assess whether 0 is in the tail or not. I really like bootstrap because it's intuitively extremely simple. And what's interesting as well is that here, for these metrics, mean or difference that we compute between our samples, we can actually use anything. We can use t-test here instead of the difference. Or if we have more than 2 conditions, we can use an ANOVA. So this is an ANOVA bootstrap. We just use the ANOVA here as an aggregator to compute a metric across these different groups. Now, you might have heard about bootstrap versus permutation. What's better? Is permutation better or is bootstrap better? Permutation is basically, it's very similar to bootstrap. The main difference is that you sample without replacement. So you can have twice the same value. And if you read Wilcox's book on robust statistics, he only has 1 page about permutation. And the reason is that from a theoretical perspective, bootstrap is more elegant and the draws are independent. So remember, we are assuming this is the distribution of our population. And if you're assuming you're drawing samples randomly, you don't want the sample you're drawing right now to be dependent of the sample you're drawing before. It's like you're recruiting a new subject, and that depends on all the subjects you recruited before. And so that's not elegant. And so that's why Wilcox doesn't like it. Wilcox recommends bootstrap. In practice, a lot of the software we use, they use permutation, they use bootstrap. In practice, there's virtually no difference between the two. So you can safely use permutation, but know that if you're a purist in statistics, it's better to use bootstrap. So now we're going to move to correction for multiple comparison, which is really central to neuroimaging methods. Because let's say we have a time frequency decomposition here. So this is our original difference. This is our original time frequency map. And then we're going to compute some bootstrap difference, let's say, between 2 conditions. So we have bootstrap number 1, 2, 3, 4, etc. But we have 1 value per time frequency point right here. So we're treating each of these independently. So first we do the distribution for the first one, then the second one, then the third one, etc. And for each of these pixels, we look whether it's significant or not. And the issue is that if we put our mask at 0.05, we're going to have about 5% of false positive. So how can we correct for these 5% of false positives? Well, there's different methods, and we're going to look at the most popular. There's Bonferroni, which is the most aggressive method, which is just divide the p-value threshold by the number of comparison. 10,000 time frequency points, divide your p-value by 10,000. Simple. It's very simple, but it's also extremely aggressive, and nothing survives Bonferroni. So then that's why we have other methods, which the first one is home Bonferroni correction. So we're going to see how this is done. We also have the false discovery rate, the max method, and finally the cluster method. So first, important concept when you compute correction for multiple comparison is the family-wise error rate concept. The family-wise error rate is the probability of making at least 1 error when performing multiple hypothesis tests. So if you put your family-wise at 0.05, what's the probability of making at least 1 error? And so, for example, you do 1 test, well, the likelihood of making an error is about 5%. You do 2 tests, it's about 10%, a little lower. You do 20 tests, it's about 64%. So this is your family-wise error rate. And we want to control this family-wise error rate. And to do that, there's the home Bonferroni method. And so here, let's imagine we don't have 10,000 value, we just have 10 p-values. You can put 10,000 on the screen. And so here we have the actual p-value, And we want to know whether these survive correction for multiple comparison. And what we do is that we draw here a linear gradient from the Bonferroni level, which is 0.05 divided by 10 here. So this is pure Bonferroni. So if we were just using Bonferroni, we would compare every single p-value to this one, the top one. And on the bottom one is the uncorrected one. And then we have a linear, we have a gradient between the two. And the home, we just do pairwise comparison. The first one gets compared to Bonferroni. Second one gets compared to one that's a little bit less aggressive, etc. So that's also a very aggressive measure, as we'll see. So for this reason, there is an alternative method that also use this type of gradient between pure Bonferroni and uncorrected Bonferroni, but it works slightly different. So this is the FDR procedure, false discovery rate procedure. With FDR, so again, this is our difference. We look at the first one that's going to change sign right here. So this one is the first positive, and then we set our FDR threshold to this value. So this is our corrected p-value threshold. This is the uncorrected one, and with FDR, this is our corrected one. And it's different from Holmes. So here the two are represented, and this is basically the different threshold which are applied to the first 10 p-values. You see Holmes is very aggressive. It's as strong as Bonferroni for the first ones, while FDR is much more lenient. And what's important to understand here is that they correct for different things. So Holmes-Bonferroni, it really controls the family-wise error rate. So we have less than 5% of having one false positive. FDR doesn't control for family-wise error rate. Instead, we have at most 0.05 false positive. So for example, we have 40% chance of observing one false positive if we have 100 values. So these are different types of correction. In practice, FDR is widely used in the neuroimaging community when you don't use the MAX or the cluster method. So the MAX method, represented here, is conceptually different. Is that we have our difference for every single time frequency point here, and we're not going to build a distribution for every single time frequency point independently. We're going to build a distribution for all of them at the same time. So we compute all our differences, and then we take the max here. What's the max difference? And this is the histogram of the max statistics. Could be the max difference, could be the max t-value. Same for difference 2. We take the max across all these values. And when on the original difference here, we test every single value here against the max. So the first against the max distribution. So this one, for example, lie in the bulk of the distribution. It's going to be non-significant. These two will be significant because they lie in the tail of the distribution. So again, one distribution for all the time frequency point in that case. And you can use the max of the statistics. You can also use the mean p-value and you compute parametric statistics on these maps. Now we're moving to one of the last one, which is the cluster correction for multiple comparison. And this one is conceptually similar to the max, except we're not going to take the max of the difference. We're going to look at the region of significance under parametric assumption. So here we set our value. We said, let's use parametric statistics. We set our value at 0.05, for example. And then we look, what's the largest region that's significant? And then this is the distribution of the size of the largest region. So for example, in the center, we might have the largest region is 20 pixels. Here, it's more of 100 pixels. Here might be 3 pixels. And then what we do is that we look at our original difference, and we look at all the regions of significance. So for this, you need some image processing to find, okay, what's the region? What's the size of the region? How many pixels in that region? And then we look if it's in the tail or not. So this is the cluster correction. Here is an example. This is the ground truth. This is the mean. We add some noise. This is uncorrected with 0.05 threshold, and this is corrected with 2 cluster. You see that it can recover the 2 cluster and remove most of the noise due to the uncorrected statistics. This can be applied to 2D images, time frequency image. They can also be applied to a single, like for example, this could represent an ERP, and here we see the uncorrected regions of significance, the Bonferroni corrected, and the cluster-based method. By the way, this method was first developed for neuroimaging community by Maris and Oostenbelt. So our very own Robert, present here, developed this in 2007. Also, an interesting characteristics of this method is that it doesn't have to be neighboring points in time frequency. So it doesn't have to be necessarily in Euclidean space. So for example, here, we can define a channel neighbor matrix. We can say, okay, what are the neighbor of this channel right here, C3? Well, this is the group of channels which are the neighbors. So we get this channel neighbor matrix, and then we can do the cluster in that space of neighboring channel. So it doesn't have to be contiguous in the time frequency plane or in the time plane. We can also look at continuity. We can look at clusters based on this channel neighbor matrix. And why it's interesting is that here, for example, we can say, okay, these groups of electrodes are significant, while these are not. This is a cluster that's significant. So that's one very powerful feature of this method. And finally, the last method, which is inspired from the cluster method. One main issue with the cluster method is that you set your parametric statistic threshold at 0.05, and basically the main result is like, these are your significant clusters, these are your these are the non-significant region, and that's all you get. You don't get, okay, this is significant at that level, for example. So to do that, there is the TFCE. It's a mouthful, threshold-free cluster enhancement. So if we have a t-value, we're going to try to build it's a method to basically enhance the t-value so we can use standard statistics on the t-value. And the way it works is that, so this is our t-value. This might be time, this is time course. And we're going to look at the size at different thresholds. So we look at different heights, and for each height, we have a multiplicative factor. And we compute the TFCE metric, which is going to be highest for these points on top and lowest for the points on the bottom, which are not part of a cluster at a higher level. So here it's illustrated. You see how the extent influence basically, for these points right here, for these points, it's part of all these clusters. So it gets all these additive terms, and the points at the lower level right here is going to only get a few of these terms. How these factors determined? So this is from this original paper. They were determined experimentally, basically. And so this is an example. So here, this is the original t-value curve, and this is our TFCE value. So threshold-free cluster enhancement. It's enhanced. So all the t-values are enhanced based on whether they belong to a cluster or not. And then we can apply standard, statistical threshold on this. And the advantage is that we can get the actual p-value if we want it. Here is an example of these methods applied to data. So this is uncorrected. So these are, for example, different EEG electrodes. And you can see, compared to Bonferroni-Holmes, almost nothing survives Bonferroni-Holmes. FDR, we have a bit more regions. and cluster and TFCE, we have the least conservative method, while still controlling the family-wise error rate appropriately. So these are the methods which are used. They are in most software. TFC is the one that's the most recommended. There's a bunch of reference, again, the book from which this is taken. And now I'm going to move to the second part of the talk, which is general linear modeling in EEG. And this is inspired by Cyril Pernay, which is a statistician, University of Copenhagen. I'm not a statistician. I'm just a user interested in statistics, because statistics is crucial when you report your data. So the GLM family, so general linear models, you do a t-test, it's a GLM. You do an ANOVA, it's a GLM. Multiple regression, it's a GLM. So we're going to see exactly how that works in a simple example. So first, a regression is a linear model. So here are, this is experiments I did a while ago. We varied the luminance of the image and we measured reaction time. How does the luminance of an image influence reaction time to detect an animal? So you just have to press a button when you see an animal. Do you go faster when there's more luminance? Yes, you do. And so this is represented here. This is reaction time. This is luminance attenuation. And we see reaction time is lower when there's less luminance. So our experimental measures is X here, luminance. We collect data, reaction time, and our model is just a regression. So it's beta 0 intercept plus the slope times our metric, our measure. We do some math, and then we get, for example, reaction time estimates 23.6 times plus 2.7x. We get this line. Okay, standard regression. Can't do it simpler. Now, if we look in detail, for each trial, this is what we have. We have reaction time, beta 1, 10 beta 2 plus, because that's the level of luminance for the reaction time 1, plus first error. Reaction time 2, might be a different luminance plus second error, etc. And so we're trying to optimize basically beta 1 and beta 2 under this constraint. And that's the definition of GLM, general linear model. And basically to know if beta 1 is significant, if the slope is significant, what we do is we compare a GLM where we have this term and a GLM where we don't have this term. And we look at the fit using R-square. And if the fit is better, significantly better, we can say, well, here the slope is significant. So this is a GLM. So a regression is a GLM. It's not approximately a GLM. It's exactly a GLM. What about ANOVA? So in this experiment, we also had different types of image. We had fish, birds, reptiles, and of course, no animals. So for example, is the reaction time different for fish, birds, and reptile? When you see a snake, you tend to respond a little faster for obvious reasons. And so we can model this using this equation in which the beta I is for each of the treatments. So we have beta 1 for fish, beta 2 for birds, beta 3 for reptile. So reaction time, for example, for trial 4 could be, okay, constant term. And here, these are birds. So we have beta 2 plus our error terms here, error 2. For trial 2, we might have another fish, and we have a different error terms. So we have all our trials, hundreds of trials. Some have 0 for beta 1, some have 0 for beta 2, some have 0 for beta 3, depending on the category. And this is a linear model. And so if we compare the model that doesn't have this beta 1, beta 2, beta 3 versus the model which has, then we can compute whether there is an effect of these variables. And this is strictly equivalent to computing an ANOVA. So an ANOVA is a general linear model. Now, the cool trick is I can put the two together, no problem. Reaction time now is based on the categorical variable, whether it's a fish, bird, reptile, plus the luminance of the image. And so I just add, my regression term from the first time. And now it's an ANCOVA. Okay, that's simple. And you can have as many terms as you want, as many variables as you want. So a general linear model is truly the ultimate linear model. So what we usually do in neuroimaging is that, okay, you have these equations, one per trial. So for example, Y, 1, 2, 3, here we have 4 groups, would be, so we have beta for the first group, beta for the second group, beta for the third group, etc. So we can write all these linear equations basically for each of the trials. But usually it's written in a matrix form, which is 100% equivalent. So it's written like this, where our observation, here, for example, reaction time, is equal to matrix time beta factors plus error. And it's the same as writing these equations, except we write it in the matrix form. And then what you will see in a lot of papers, in this matrix of 1 and zeros is not represented with 1 and zeros. It's represented like this, with white cells and black cells. So when you have white, means 1. When you have 0, it means black. And this is the design matrix of your data. It's a central concept, and you'll see it often in both EEG, MEG, and fMRI. So the design matrix, so once you have your design matrix, here if we had a continuous regressor, for example, luminance, it would be shades of gray here, because the luminance doesn't take just 0 and 1, it can take different values. So that's what's represented here, for example. So this is our electrode number 1. Here is our design matrix. We have all our different trials, and then we're going to apply our GLM at a given time point. And here it's, some trials are stimulus 1, some trials in the bottom are stimulus 2, and all the trials have a different noise level. So here we have our continuous factor. And then we also always have a constant in the model. So we apply this, and we apply this at time 1, then we do it again from scratch. Time 2, time 3, time 4, time 5, time 6, etc. And then we can get the time course of our beta parameters. So when these are categorical variables, so this is, for example, beta 1, beta 2, beta 3, and then we can do stats on this parameter. Is beta 1 statistically different from beta 2? We do bootstrap analysis, where we bootstrap the trials, and we compute our beta, and we can get confidence interval for this beta. And if we want to compare condition 1, for example, stimulus 1 versus stimulus 2, we just do the beta from stimulus 1 minus the beta from stimulus 2. So it's a shift in thinking to compute the statistics on the beta, but often what we do is, so you can do that for one electrode, you can do that for all the electrodes, again, independently. You do that independently every single time points, every single electrodes, and you can get your scalp topography. You can use the cluster methods to find the regions of significance, and you can either show the scalp topography of the beta difference, for example, between condition 1 and condition 2. But if you're used to showing the difference between the two conditions, like the difference in potential, for example, it's fine. You can show the difference between potential and the mask. You use the mask based on the statistical inference you draw from your beta statistics. Okay, so it's the same threshold. Here we show the beta, or we show the difference between the potential. Either is fine. Now, you can actually build different design metrics based on the experiment you're doing. And these are examples. So let's say we have 4 types of stimulus. Red disk, green disk, red square, green square. And this is our most simple design matrix. Some trials are the red disk. Some trials are the green disk. So here we have a bunch of trials. Some trials are the red square, sometimes are the green square. Alternatively, we can also have a design matrix that looks like this. Some trials are circles. So these are all the first ones. Some trials are not circles. Sometimes are square. Some trials are red, and some trials are green. So which one is better? It's called the interaction design here. Obviously, it's called a factorial design. Which one is better? Well, they're virtually equivalent, because here, once you're done with that, you can do a subtraction between your beta, basically to obtain the same type of contrast. If you're interested in the circle here, you would subtract beta 1, but you would compare beta 1 and beta 2 versus beta 3 and beta 4. If you're interested in the color, you would compare beta 1 and beta 3 versus beta 2 and beta 4. Here you have it right away. But they are virtually equivalent. Now, what's slightly different here is that you can build interaction at the subject level. So this is called a full factorial design, in which you model the interaction as well. And we'll come back to this in a second. This is, there's no right and wrong, by the way, here. You can use either of these. The important is to understand the slight difference between these different models. So the basics of this type of analysis is hierarchical modeling. So you do that for every single participant, channel 1, channel 2, channel 3, channel 4. Then you have participant 2, participant 3, etc. And then you get your betas. But your betas are specific to participants. And you really want to do group analysis. To do group analysis, you do a second level GLM. So you first a GLM on your participants, and then you do a GLM at the group level. And this was originally designed for neuroimaging in SPM, so for fMRI analysis. That's what made it so popular. But now, you have this type of analysis for EEG as well. So these are hierarchical model. So here is another representation. We have our design matrix at level 1 for participant 1, participant 2, participant 3. We get all our betas, and then, for example, we can do two-way ANOVA on these factor to compute main effect, second effect, and interaction. So we can get the main effect of shape, color, and interaction at the group level. Okay, so that's one standard way to do it. Or if you have a full factorial design here at for every single participant, you get the shape effect by aggregating the beta for the shapes, the color effect by aggregating the beta for the colors, and the interaction by doing one sample t-test on the interaction term at the subject level. And both are equivalent, basically. If your participants are homogeneous, there's not like one participants that have special effect. They are returning very similar results. So now you may wonder, like, that sounds very complex. I mean, why do I need to do a GLM first level, GLM second level? Let's just me apply a GLM on all my data. And that's very possible. It's called a mixed effect model. So now you have some trials that belong to participant 1, participant 2, participant 3. And this is called your random effect. So these are factors, but they're modeled slightly differently compared to the fixed effect. And this is a standard thing in statistics, the mixed effect model. So what's the difference between a mixed effect model and a hierarchical GLM? What's best? Well, Cyril showed that the two are roughly equivalent. The reason we use hierarchical GLM for neuroimaging is for two main reasons. First, it's much more computationally tractable. Here you might have like thousands, hundreds, maybe dozens of thousands of trials across all your subjects. It just doesn't fit in RAM. You can't just apply the statistics, just too much data. So that's why hierarchical GLM makes sense. Also, the advantage of the hierarchical GLM is that you can easily you can process each participant independently. So you can go back to each participant and investigate the beta independently. Now, this is all good and well. What do we do in practice? In practice, this is what I recommend. The recommend is more, for everyday use, I recommend using the mixed effect model, just from the command line. So this is how you define a mixed effect model. So you have your variable of interest. Here, it could be the group of your subjects, reaction time, any measure you can have. And then you have categorical variables like gender, continuous variables like you have age of the participants. And here I put an example, the spectral power of electrode CZ at 10 hertz. It's just an example. And then you have your random effect. So this is how you indicate the effect of the subject. So this is how basically you define this matrix in statistical model. And you just enter this equation I'll show you what kind of function you can use. So for example, trial 1 for subject 1 would be the gender of subject 1 plus the age of subject 1 plus the spectral of power of subject 1 for trial 1 and subject 1 plus the constant for subject 1 plus the error. And then same for the trial 2 of subject 1. Trial 1 of subject 2, now we have the gender of subject 2, age of subject 2, spectral power at CZ 10 hertz for subject 2, etc., and the constant. And this is one line of code. This is how to call here. You give your data. The data is a table. It's in matrix DF, and it has this column defined, gender, age, spectral power. And this is how you call it in MATLAB, PGLM E. This is a mixed model. This is how you call it in Python. You just give your data as input. This is how you call it in R. And if you have a categorical variable here as the output, like for example the group of subject, then you just add this distribution binomial, and you can model any categorical variable. It's that simple. And it's very important to use these models because, especially in neuroimaging, gender and age has very strong effect on your data, so it's important to include them in your model. Now, an issue is that, here it was spectral power CZ 10 hertz. What about if I do it for all the electrodes and I do it for all the frequencies? Well, then you have to correct for multiple comparison. And what do you use? Well, you use our good old TFCE method. So in MATLAB, we have the LIMO TFCE method. You just enter this matrix of either p-value or statistical value, and it's going to correct, it's going to find your clusters for, across electrodes and frequency, for example, in this case. There's the equivalent in Python. It's a little bit more limited because it's based on sign test, but it's basically the same principle. So what's the advantage? I mean, why do we even have this advanced software? So in EG Lab, we have LIMO that models all these trials. Why just not do it like this? You just scan the time, compute your model for every single time points, and you're done. Well, you could. That's ordinary least square, so that's one of the options in LIMO. But the advantage of the software that looks at all your data is when they can weight trials. So if you have outlier trials, it's going to consider, okay, all these values for this trial is an outlier. Let me weight it down. Okay, these methods don't weight trials. Okay, actually you can add a weight factor. So if you compute the weight factor, you can weight the trials. But basically, if you have to compute the weight factor, you might as well use the software that does it for real. So the advantage of using software that basically processes all your data in a hierarchical way versus using just a mixed model on your data is that you have additional bells and whistles to handle outliers, basically, and weight down the different trials. So that's the end of my presentation. I hope it was useful and will improve your statistical skills.